A single-phase induction motor with this equivalent circuit and parameters, we have to calculate the power factor and the source current. We have to calculate the forward and backward counter EMFs. And lastly, we have to calculate the forward and backward series component currents. For the purposes of this problem, we are applying a voltage of Vs, which is equal to 240 volts, and a load is such that it is causing a rotor slip, SF, of 0.036. Previously, the forward circuit impedance, ZF, has been calculated to be 12.05 plus J, 24.67 ohms, and the magnitude of which is 27.45 ohms. ZB has been previously calculated to be 1.49 plus J, 3.89 ohms, and the magnitude of which is equal to 4.17 ohms. The total motor impedance, ZT, as seen by the applied voltage, is equal to 13.54 plus J, 28.56 ohms, and has a magnitude of 31.61 ohms. The calculation used in the determination of the total circuit impedance, ZT, is the sum of the forward impedance, ZF, in series with the backward impedance, ZB, which in real terms is 12.05 plus J, 24.67, plus 1.49 plus J, 3.89, which adds up to 13.54 plus J, 28.56 ohms in rectangular coordinates, or 31.61 at an angle of 64.63 degrees in polar coordinates. The power factor angle due to the load, ZT, is equal to the inverse tangent of 13.54 divided by 28.56, which works out to 64.63 degrees. The power factor then is the cosine of that angle, which is 64.63, which equals 0.43. Now, in order to calculate the source current that the motor draws, it is given by the applied voltage all over the magnitude of the total impedance, or 240 divided by 31.61, which works out to 7.59 amps. The forward and backward counter EMFs are simply the voltage measured across both of the forward and backward rotating circuits. In order to visualize this more simply, I am again going to lump the forward and backward impedances and call them ZF for the forward impedance and ZB for the backward impedance. Now we can simply use the voltage divider rule coupled with the applied voltage in order to calculate the forward and backward counter EMFs, starting with the forward counter EMF. It is given by multiplying the applied voltage Vs by the magnitude of the forward impedance divided by the magnitude of the total circuit impedance. Now, inputting the real values, we get 240 times 27.45 divided by 31.61, which equals 208.4 volts. For the backward counter EMF, we multiply the applied voltage Vs by the magnitude of the backward impedance divided by the magnitude of the total circuit impedance. Now inputting the real values, we get 240 times 4.17 divided by 31.61, which equals 31.67. Our last task is to calculate the forward and backward component currents I'(SF) and I'(SB). These are the currents through the series components of the forward circuit and the backward circuit. We are first going to calculate the forward series impedance, which is made up of the stator resistance plus the rotor reactance reflected to the stator side plus the stator reactance. In actual terms, it is 1.6 divided by 2 plus 4.43 divided by 2s plus j 8.71 divided by 2. We know that the slip S is equal to 0.036, and therefore this equation can be calculated, and it gives us 62.2 plus J 4.34 ohms. The backward series impedance, which is made up of the stator resistance plus the rotor resistance reflected to the stator side plus the stator reactance. In actual terms, it is 1.6 divided by 2 plus 4.43 divided by 2 times the quantity 2 minus s plus j 8.71 divided by 2, which when calculated gives us 1.93 plus j 4.34 ohms. These two impedances are in rectangular coordinate formation, and we need to know the magnitude of the forward and backward impedances. So we will use the Pythagorean theorem to calculate the magnitude of the forward impedance, which is the square root of 62.2 squared plus 4.34 squared, which equals 62.36 ohms. The backward impedance is given by the square root of 1.92 squared plus 4.34 squared, which equals 4.75 ohms. We are now in a position to be able to calculate the component currents in the forward circuit and in the backward circuit. Starting with the forward circuit, I primed SF is equal to the forward circuit back EMF divided by the series impedance of the forward circuit. Plugging in actual values, we get 208.4 divided by 62.36, which is equal to 3.34 amps. The backward circuit, I primed SB is equal to the backward circuit back EMF divided by the series impedance of the backward circuit. Plugging in actual values, we get 31.67 divided by 4.75, which is equal to 6.67 amps. And so we have come to the end of our problem, because we have completed the 3 tasks that we set out to do. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site, my stand store for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB. Before ending, I wanted to make you aware of this special offer. EcoFlow's most powerful innovation yet, the Delta Pro Ultra X, has officially launched in North America. This early bird event brings massive savings to you. Exclusive early bird deals are available from November the 3rd to November the 30th. Customers get up to $1,000 off for those who have paid the deposit, or an extra $300 off with a special code DPUXAF300 for non-deposit users. In order to take advantage of these offers, simply go to this web address in the United States, https://bit.ly/47 uppercase P, lowercase l, lowercase I, lowercase c, and uppercase G. And go to this web address in Canada, https://bit.ly/for lowercase q lowercase s uppercase E uppercase Q lowercase u uppercase O.